Fighters like the F-4 Phantom were the norm, but the F-4 found itself in peril frequently, at a significant disadvantage when taking on the smaller, maneuverable Soviet-made MiGs of the Vietnamese Air Force, like the MiG-21. The MiG-21 was a small, single-engined, lightweight aircraft with thin delta wings. The F-4 was fast, flying up to Mach 2.2, travelled further, and carried more missiles, with a powerful radar. But its lack of maneuverability at low speed, poor pilot visibility, and easy identification due to jet engines that billowed black smoke trails made it vulnerable to sneak attacks from the Soviet interceptor. MiG-21s frequently flew close to the ground, under radar, and ambushed incoming F-4s, making a single attacking run with their ATOL infrared-guided missiles, and then using their low-speed maneuverability to outturn and escape. From August 1967 to February 1968, US losses in Vietnam were staggering, losing 18 aircraft while downing just 5. For a nation accustomed to absolute air superiority, something was off. The MiG-21's introduction in 1966 forced the US to adapt. Its large heavy fighter bombers, while useful, were at a disadvantage against these smaller, cheaper planes, and something needed to be done. The Red Barn study, commissioned by the US military, began to identify and address the tactical and technical issues causing the heavy losses that both the US Navy and Air Force were experiencing in the Vietnam War. And their findings led to the development of one of the world's most ubiquitous fighter planes, a plane designed with a new, physics-based doctrine at its core. Entering service in 1978 and standing the test of time, it is now confirmed that the aircraft will be entering the battle for Ukraine's freedom, taking on the modern-day counterparts of the MiG. This is the insane engineering of the F-16. The F-16 was built from the ground up with this classified 1966 paper as its guiding light. A paper full of mathematical models, graphs, and equations designed to answer one question: how to win a close-quarters dogfight. Created with the help of military supercomputers, it defined a new concept: energy maneuverability. Created by Colonel John Boyd, an Air Force veteran of the Vietnam War, and one of the members of the so-called fighter mafia, with the help of a civilian mathematician, Thomas Christie. These graphs were the basis for defining a plane's maneuverability through its full range of speeds: Mach number on the x-axis, turn rate on the y. A theory underlined by the management of both kinetic and potential energy, speed and altitude. In order to change direction, a fighter aircraft must trade energy from these reservoirs, and doing it as efficiently as possible is the key to outmaneuvering an enemy. This is the energy maneuverability diagram for the F-16. It's a complicated graph to read without some basic understanding. This line is defined by the maximum lift of the aircraft. This is important because it determines the maximum turn rate at a particular speed in this region. We need lift to turn. To begin a turn, an aircraft will roll in the direction of the turn. This splits the lift the plane is generating into two components: a horizontal component that causes the plane to turn, and a vertical component that keeps the plane in the sky. A steeper bank angle will increase the horizontal component and increase our turn rate, while stealing lift from the vertical component. This vertical component needs to equal the weight of the aircraft, or the plane will lose altitude. To compensate for that, the pilot will need to increase lift by increasing the angle of attack. This is where the maximum lift issue arises. More lift means more available force